Welcome back. So as we come close to the first part of this course, um, which mostly focused on basic definition of this notion of stability, and then how to check for the stability using the famous method of Lyapunov, right? The difficulty also is basically how to find this Lyapunov function, and in that sense, it's both fantastic and also problematic, right? I mean, you have this beautiful notion that theoretically, more than 100 years old result that says that if we can find this Lyapunov function, then we are safe, right? We can do everything that we want. We can conclude. So this particular lecture and even later part of the course, the second part of the course, will focus a bit on class of systems where we can actually show many results relatively easily by actually constructing certain Lyapunov functions and things like that. But this particular lecture is specifically geared towards identifying special ways of constructing these Lyapunov functions. These are very special, limited in nature, and then one mesh procedure goes towards that, but it's still not there. In that sense, the problem of finding Lyapunov function is an open problem, and then there's only so much we can do. But of course, don't really have a choice there, right? So anyway, this lecture is going to first talk about something called gradient systems, then very specific method called Krasovskii method, followed by a method called method of Zubow, and finally, an upcoming method. It's most recent 20-year-old method called sum of squares method, which I will just give the idea here and then not really get into too many details. In some sense, it's a straightforward method to understand. To implement it is another thing, right? So let's actually first critique Lyapunov methods, and we have kind of mentioned this many times. I'm just formalizing and summarizing all the points that are there in regards to this Lyapunov notions of first the definition of stability itself and then the method, right? And I think I mentioned this again and again, and most recently in the last lecture, is basically the Lyapunov stability notion is essential in that sense. You cannot have any other notion. If you want some kind of notion of perturbation from equilibrium starting close and remaining close, you cannot avoid this epsilon delta things, right? So accordingly, then of course you'll have this convergence is much easier to understand, but combining both of them will give you this asymptotic stability, and that's an important feature that we want for a general system, nonlinear system, right? So you can have this bounded input, bounded output stability notion, or boundedness and things like that. Some of them are less restrictive, but something like bounded input, bounded output depend on this very complicated epsilon delta definition. And one can actually extend these definitions to include randomness, stochastic nature, and things like that. And you may have corresponding analogs in discrete time, hybrid systems, and so on and so forth. But all of them, in some sense, go back to this definition by Lyapunov. You don't have a choice but to accept that definition as gospel, right? So then how do we check for that stability? And then we actually started with Lyapunov's direct or second method, and then basically we went to the indirect method. But indirect method is quite easy, where basically we simply linearize the system, this f of x, and then basically find the so-called p matrix that we have seen, and that p matrix will provide x transpose px, the Lyapunov function. But of course, that proves only local stability, and anything that has kind of essential nonlinearities or limit cycle behavior and things like that, that method is quite useless. And as we have seen, basically even Lyapunov stability cannot be shown through linearization. But the direct method is much more useful. But finding Lyapunov functions, so far we have seen a bunch of examples, but there's no generic method in terms of how to find Lyapunov functions, right? As I was indicating, sum of square methods that I will introduce later is quite powerful in terms of the computational aspect, but beyond that, there is no general way of doing it. These days you'll see research, ongoing research on basically finding Lyapunov functions through neural networks and things like that, which indirectly relies on the sum of square method, but nothing more general than that. In that sense, it's an open problem, right? I mean, when we say it's an open problem, it is still an art in terms of finding Lyapunov function and things like that. So most of us who pursue career in, let's say, nonlinear systems and control, one has to essentially develop this practice, develop the art of actually finding these Lyapunov functions. So more systems you actually chose to work with, basically you have better ways of finding these Lyapunov functions, right? And there is some method to this madness, but not really, right? This sum of squares or whatever, they help a little bit, but sometimes the sum of square kind of methods also may not shed insights into the system, and then there may be a slightly more natural way of deriving the Lyapunov functions, right? So this is only analysis, right? And if you're trying to basically solve a problem involving control design, feedback design, then basically you'll have additional parameters coming from design that are to be chosen. So not only you have to find a Lyapunov function for this control problem, but you also have to find the controller, the control function itself. So you have additional variables that we have to find simultaneously. So one has to find this Lyapunov function that satisfies all these conditions along with finding this phi. Together they should satisfy the Lyapunov conditions that we put forth. So in that sense, it's simply put, basically solving a nonlinear control problem remains an art. There are some generic methods, and these days therefore people kind of are moving towards more machine learning methods, but machine learning methods have their own serious problems, right? I mean, they don't provide any guarantees in any sense. So let's look at some of these different methods. The first one is gradient system. It's a very straightforward observation, I would say. So let's say somehow we have this function v, which is connected very well with f of x. Okay, so v happens to be the Lyapunov function candidate in the sense that v of 0 is 0 and v of x is positive for all non-zero x. And miraculously, let's say f of x happens to be equal to minus the gradient transpose of x, right? If you recall, the gradient itself, v of x is v prime of x is, I said, it's partial derivatives of v with respect to x1, x2 in a row vector. So you put the transpose and you put a minus in front, and then basically that becomes your f of x, right? And in that particular case, you can clearly see the v dot is simply going to be minus v prime times v prime transpose, which is basically you're taking squaring a function, so to speak, in a vectorial sense, and that's going to be always going to, the square part is non-negative, where the minus part will give you non-positive. So v dot is going to be less than or equal to 0, and that's it. We are done. If we can, if we have this particular property, f of x happens to be equal to minus v prime transpose for some non-negative definite function, positive definite function v, then we have Lyapunov stability, and then anyway we can get asymptotic stability also if we can somehow show that it's strictly less than 0. But you can use Lassalle's theorem to also show asymptotic stability, right? And if you have radial unboundedness, you may have guarantee of global stability and things like that, right? So this result may look really funny in the sense that, okay, fine, you're making the theory work by choosing your system itself in a certain way, in this abstract manner, right? But in reality, the original discovery of Lyapunov function theorems itself may have gone back with this kind of understanding, where this f is actually coming from some energy function. In physical systems, basically, loosely speaking, f, we can think of it as a forcing function. Not quite, because typically as soon as we say force, we have a second order differential equation, but live with it for the time being. Let's say I'm going to call f as forcing function, And the forcing function is going to be typically a derivative of some kind of potential energy function, right? And when that happens, basically the potential energy gives you what you call non-negativity naturally, and everything is going to be nice, right? So in that sense, this is not something that's out of norm, and in fact this is of our mechanical systems. At some point we will look at some of those details. You know, this kind of understanding will lend itself to naturally to a Lyapunov function, right? So we'll go through some of these details, right? But let's say we are dealing with a more general system, then basically somehow if we can figure out this f to be related to some kind of gradient, then you know, perhaps we have a hope in terms of discovering the corresponding Lyapunov function. So that's what we will look at next, basically a general gradient system. The first system is like more restrictive, useful for mechanical systems, but this is now in the mathematical world where you have a generic f. Okay. Now, given an f, somehow we know that we could find some function g when we basically take the inner product between g and f. It turns out to be negative, let's say, right? Negative definite, I should say. Now, can we construct function v such that v prime is g? If we can, then basically we'll have stability, essentially, right? So the question then becomes, is basically given a function, I mean, you know, finding you know, one way of doing it is g is equal to minus f, for example, right? So that is more than enough, like in the previous case. Now, under what conditions can a generic function f become a gradient of some other function, right? Gradient is simply basically, if you take a scalar function, you take this you know, partials with each of these things. That's what is we call it as gradient. So if you have a vector function, right, a function of a bunch of x1, x2 and things like that, you have a vector of them, under what conditions can we guarantee that it becomes a gradient of some other scalar function, right? So interestingly, the answer is relatively straightforward, and it reminds us of many such conditions. I don't want to really get into any of those things, but you know, Cauchy-Riemann conditions, for example, will guarantee certain things and things like that. So it kind of reminds you some of those standard conditions that we see many times in mathematics, right? So there's this interesting fact that g of x is a gradient function. That is, there exists a v of x such that g of x is going to be equal to the gradient of v of x if and only if for every I and j this cross derivative of g, not v, cross derivative of g is equal to one another, right? So partial of gi, the ith component of g with respect to jth component of x, it should be the same as derivative of jth component of g with respect to ith component of x. And why is this true? I mean, you know, in a way, very high, at a high level, basically, when you substitute v there, it simply becomes the second derivative. And then if you have a you know, twice differentiable function v, then basically this is automatically satisfied, right? So, but it becomes necessary to find such a gradient function. So that's one of the things. So we should not only look for some g that satisfies g transpose f less than 0, but we should actually be looking for functions that satisfy this condition. The native f may not satisfy this particular function, and then basically you know, therefore we have to impose this particular condition. Okay, so you know, if we have it, then we can find v, right? So how do we find such a v? I mean, there are several ways of doing it. One nice result about this gradient functions are basically from gradient function, if we actually you know, take some kind of line integral, basically the fact that this g is a gradient of v guarantees that basically the specific line integral that we choose, you know, the path we choose from two extremes is, you know, 0 to x, let's say, where x is a vector, 0 is the origin. We can imagine a path between 0 and x, and then integrate on that particular path, and then we can actually get v of x, right? So the nice thing is that all such integrals are path independent, so we chose a particular path, and it's not necessarily that we have to use this kind of approach to derive v of x, right? So, we satisfy this particular necessary and sufficient condition for a function to be gradient. Once we get that, we simply integrate this. This is a scalar integral, so to speak, right? If you can see, basically G transpose is a vector function multiplied by x. In the product will give you a scalar function of x, but the variable that we are integrating is basically sigma, and then sigma can be integrated out, right? And when we do that, we'll get our v of x. Now, none of these things guarantee in any sense that v of x is going to be a Lyapunov function candidate, in the sense that the first condition G transpose f less than 0 gives you the second derivative. V dot is less than 0. This condition that we see here guarantees that you can find a gradient, right? And then the integration will give you the scalar function v, but it does not guarantee that v is in any way positive definite, right, for it to be a Lyapunov function candidate. So that's a problem that we have to deal with. Okay, so in the previous case we assumed that basically somehow function is directly related to a potential function. Here we are saying basically if somehow we can find this g such that when you integrate it you get v, and then if you are lucky enough that v is positive definite, then we can guarantee asymptotic stability, right? So that's the method. And then in lack of any great ideas, general ideas, this is a fantastic idea in my opinion, motivated by physical systems. So which also means that basically there are many systems where this can actually work out quite well, right? So here is an example. Basically you have this x1 dot is equal to x2, okay, and x2 dot is equal to some x1 plus x2 and then minus sine of x1 plus x2, and we're trying to find whether this particular function is asymptotically stable or Lyapunov stable, whatever it is, and can we find a Lyapunov function, right? We have no idea. So how do we go about doing that? Of course, one simple thing is actually perhaps look at it from a linearization perspective, and then you can clearly see that this linearization will produce indeed stable system, and I'll demonstrate that. I mean, I want you to note that sine of theta for small values of theta basically approximates to theta, so keep that in mind. And then so we have therefore x1 dot x2 dot is equal to, we have some sine function and things like that, and you will essentially get this, okay, 0 1 minus 2 minus 2, right? And if you recall, I mentioned that basically the trace of given a 2 by 2 matrix, we have to check if the trace is less than 0 and determinant of A is positive, and if both are true, then we can basically get to conclude that this particular matrix is Hurwitz, and therefore the system is stable, right? So what is the trace? Trace happens to be minus 2, and determinant happens to be 0 minus 2 will give you 2. So this particular system is going to be Hurwitz, right? I mean the matrix is Hurwitz, so this particular system is going to be linearly stable. I mean the linearization is stable, therefore we can use P matrix coming out of that linear system to actually use it as a Lyapunov function. Now the question is, can we actually say something more beyond some small local region, right? So the method we are going to use is the gradient system example, approach that we chose. So I'm going to choose some g of x to be this. Why did I choose that? The specific examples, you'll develop intuition that something may work out simply because this approximates to x1 plus x2. Perhaps a simple linear, most generic linear function can help, right? So one of the first things that one notices is basically, is this a gradient function? And for this to be a gradient function, you'll immediately conclude that a12 and a21 has to be same. Otherwise, we'll not satisfy that partial of g1 with respect to x2 and partial of g2 with respect to x2 both have to be same. So that's one of the first things that we do. We simplify this very generic linear vector function to satisfy that these two parameters are the same, right? Once we have that, we can compute g transpose x, and then we'll get this complicated looking function. And by observing it, by essentially looking at carefully, how can we make this less than 0 is what we are going to think of. And then there are multiple ways of doing it, and then basically we will choose our a11 and a22. Those are the only two parameters left now in terms of beta, and then we will eventually end up with this nice looking minus beta x1 square minus beta of x1 plus x2 times sine of x1 plus x2. Now we know that this x1 plus x2 times sine, okay, is negative if x1 plus x2 is between minus pi and pi, right? And so that's much bigger region than what local notion of linearization will provide. In that sense, this is far more global in sense than the linearization result that we had earlier, right? So, and how do we get this v of x? V of x is simply integrate it out, and then I'll leave it as a homework to verify this particular calculation, but we will end up with beta x1 square plus beta x1 x2 plus half beta x2 square. And is this positive definite? Well, one can easily see that if you separate it out, half x1 square, and then rest of the remaining thing, you'll have actually half of another square. So you'll have sum of two squares, sum of squares, right? So that's one of the easiest things to conclude. If you have v of x is to be sum of squares, that's going to be non-negative to start with, positive definiteness of the function. Whenever x is non-zero, whether it's going to be guaranteed to positive, then that's an additional check, right? So here is an example where we started with the general system, and then we kind of forced this gradient g of x to satisfy certain conditions, but we started with a very generic g of x and chose these parameters a11, a22 and things like that to satisfy first this gradient assumption. The second one is basically then the negativity assumption, and finally integrate it out to get your nice Lyapunov function. But of course, we've been lucky that basically this v of x is positive definite. There's no reason that going to happen always. So different examples, you may have to try out these kinds of things in multiple different ways and hope to find an answer, right? Sum of squares essentially is a method where you're looking for such functions in a polynomial sense, okay?